Ever wondered how AI models like GPT or BERT can understand language so profoundly? The answer lies in a revolutionary architecture that's reshaped the field of machine learning, the transformer. Today, we're diving deep into the technical heart of transformers, how they work, why they're so powerful, and the cutting-edge research pushing their limits. Let's get technical. For decades, recurrent neural networks, RNNs, and their variants like LSTMs dominated NLP. But they had a critical flaw: sequential processing. Each word had to wait for the previous one, making parallelization impossible. Enter the transformer, introduced in 2017 by Google's research team. This paper, "Attention is All You Need," proposed a radical idea, replacing recurrence with self-attention mechanisms. Suddenly, models could process entire sequences in parallel, unlocking unprecedented efficiency. Let's break down the transformer's architecture. At its core are two main components: the encoder and decoder. The encoder processes input data, while the decoder generates output. But the real magic happens in the self-attention layer. Here's how it works. For every word in a sentence, the model calculates its relationship with every other word, creating a weighted representation. This allows the model to capture long-range dependencies, like understanding that it refers to a previously mentioned noun, without relying on sequential processing. Self-attention involves three vectors: queries, keys, and values. Think of queries as questions, keys as answers, and values as the data itself. The model computes a score for each query key pair, then applies a softmax function to normalize these scores. These weights determine how much focus each word should have on others. For example, in the sentence, "The cat sat on the mat," the word cat might receive higher attention from sat than from mat. This dynamic weighting is what enables the model to contextualize words effectively. But wait, how does the model know the order of words? Unlike RNNs, transformers don't have an inherent sense of sequence. To fix this, they use positional encoding. This is a set of learned vectors added to word embeddings, encoding the position of each token. These encodings can be learned or fixed, like using sine and cosine functions of different frequencies. This allows the model to infer relative positions, even though it's processing all tokens simultaneously. Since their debut, transformers have evolved dramatically. Models like BERT, RoBERTa, and T5 have fine-tuned these architectures for specific tasks, while researchers explore alternatives like the longformer and Big Bird to handle longer sequences. But challenges remain. The quadratic complexity of self-attention limits scalability. Processing a 10,000 token document is computationally expensive. Recent work on sparse attention and efficient transformers aims to tackle this, using techniques like sliding windows or hierarchical attention to reduce complexity. Looking ahead, the field is moving toward more efficient and specialized architectures. Researchers are experimenting with hybrid models that combine transformers with convolutional or recurrent layers, as well as exploring non-attention-based approaches. Meanwhile, the rise of large-scale models like GPT-4 and PaLM highlights the versatility of the transformer framework. But the question lingers: will transformers remain the dominant paradigm, or will a new architecture emerge? The answer might lie in the next wave of research. Transformers have revolutionized AI, but their journey is far from over. By understanding their inner workings, we gain insight into the future of machine learning. Whether you're a researcher, developer, or curious learner, the Transformers story is a testament to the power of innovation. Stay tuned for the next breakthrough, because the attention is far from over.